In the next 40 minutes, we'll be talking about a feature that was first introduced as a preview in Java 24, finalized in Java 25, but in the current Java 26 still needs to be explicitly enabled. We're talking about compact object headers, and not just those, but we'll use them as a starting point to explore various fascinating internals of the JVM, the Java Virtual Machine. A major tech company recently managed, simply by upgrading to Java 25 and by enabling this inconspicuous JVM option, to reduce the memory consumption of its Java landscape by 22% and increase throughput by 11%. To show you how this was possible, I'd like to take you on a journey today. A journey deep into the inner workings of the JVM. Along the way, we'll first encounter regular object pointers, the so-called ordinary object pointers, or OOPs. We'll see how these are compressed into the so-called compressed OOPs. Then we'll travel past class pointers and on to compressed class pointers. And then we arrive at the object headers. There we will take a very close look at the class word and the mark word. And for the mark word in particular, we look at how it is used for the synchronized mechanism and also what role it plays in the pinning of virtual threads. After that, we'll look at how the new lightweight locking simplifies the synchronized mechanism and how it helps prevent the pinning of virtual threads, and how it paves the way to the highlight of the journey, compact object headers. And there you'll see how the Project Lilliput team managed to compress the object header from its current 128 or 96 bits down to 64 bits, and how it is planned to be further reduced in the future to just 32 bits, a fraction of its current size. We begin the journey with the ordinary object pointers. That was my computer when I was writing my final exams. It was a 386 and it originally had 4 megabytes of RAM, and I still remember well, I was on the yearbook editorial team and we wrote the yearbook on my computer. And at some point it no longer fit in memory and I had to upgrade from 4 to 8 megabytes, which cost 400 Deutschmarks. But why am I telling you this? Many of you probably don't remember either the 386 or the Deutschmark. The 386 was a 32-bit system. That means it had a 32-bit wide bus, could process 32 bits at the same time, and could use 32 bits to address memory. So it could address 2 to the power of 32 bytes, that's 4 gigabytes. And at the time, that was an unimaginably large amount of memory. As I said, after the upgrade, my computer had 8 megabytes, about 1/500th of the maximum. Today's CPUs generally have 64-bit architectures, meaning a 64-bit wide bus, and can therefore address memory using 64 bits. This allows us to address 2 to the power of 64 bytes, which is 16 exabytes or 18.4 quintillion bytes. And to keep the proportions correct here, we need to show the RAM up above significantly smaller. That's then just this tiny dot here. And 16 exabytes, that's so much that if you used it to store a movie in 4K Ultra HD quality and watched it non-stop, it would last about 250,000 years. Which is great, but 64 memory addresses also take up 64 bits. So, as you can clearly see here, twice as much as 32-bit memory addresses. In a Java application, this means that all object references take up twice as much memory. And in cloud environments, where you pay for every megabyte of RAM, this can account for a not insignificant portion of operating costs. Now, we could consider simply working with 32-bit addresses on a 64-bit system. But the 4 gigabytes we can address this way that tiny dot up there in the middle, the 4 gigabytes that seemed out of reach when I was in school, today they're not even enough for a budget PC. And with that, let's move on to compressed OOPS. Instead of settling for one option, a maximum of 4 gigabytes of addressable memory, or the other option, twice as large pointers, the hotspot developers found a clever compromise between addressable memory space and pointer length. CPUs operate most efficiently when data is aligned to addresses that are a multiple of its size, and int, for example, at addresses divisible by 4. At the beginning of an object, we find the object header, and that in turn starts with the 8-byte mark word. And to ensure that this mark word is always correctly aligned, and in particular to allow it to be modified atomically, Java objects always start at addresses divisible by 8. Such addresses, that is what they look like in binary, always have zeros in the lowest 3 bits. Now we can take a 35-bit address that is divisible by 8 and shift it 3 bits to the right, and we would have a 32-bit value that represents the upper 32 bits of a 35-bit address. And so, with just 32 bits, we can address 2 to the power of 35 bytes, which is 32 gigabytes. And that's significantly more useful to us than 4 gigabytes. And this is exactly the mechanism implemented in the JVM, and it's called, as you can already see in the heading, compressed OOPS, that is compressed ordinary object pointers. The overhead of this bit shift is minimal. It is typically executed in just a single CPU cycle. That's why compressed OOPS are enabled by default on 64-bit systems with a heap up to 32 gigabytes. However, anyone who wants to squeeze out the last bit of performance can also disable compressed OOPS using -XX -use compressed OOPS. Then full 64-bit pointers are used with no bit shifting overhead, but at the cost of increased memory usage. More memory also means fewer objects in the CPU cache, potentially more cache misses, and that in turn can negatively impact performance. So ultimately, it's an it depends, and you need to test it for your specific application. To summarize, the default for a heap up to 32 gigabytes is 35-bit pointers shifted 3 bits to the right, compressed down to 32 bits. For a heap larger than 32 gigabytes, or if we disable compressed OOPS, we have full 64-bit pointers with no bit shifting, but they take up twice as much space. That was compressed OOPS. Next, we'll take a look at class pointers. When classes are loaded, they are stored in memory in the form of so-called class metadata. The header of every object contains a pointer to the metadata of that object's class, so that at runtime the JVM knows which class an object belongs to. A long time ago, up to and including Java 7, these class metadata objects, together with other metadata, resided in the so-called permanent generation on the heap. That was rather annoying because back then we had to manually configure the size of this generation depending on how many classes we expected the application to load. Some of you might remember this error message, out of memory error permgen space. This meant that the permanent generation was full, the application would then terminate, and we had to restart it with a larger configured permanent generation. On a 64-bit system, the class pointers into the permanent generation were generally 64 bits in size. And that's basically it. Those were the traditional class pointers. And now we move on to the compressed class pointers. In Java 8, the permanent generation was replaced by metaspace. This is an area in native memory, meaning it is not located on the Java heap. With the introduction of metaspace, the compressed class space was also introduced. This is a separate area within metaspace that is reserved exclusively for class metadata. At first glance, compressed class space sounds as if the class metadata stored there were compressed. But that is not the case. What is compressed are the class pointers. However, the compression of class pointers works differently than that of object pointers, the compressed OOPs. Class metadata is typically between half a kilobyte and 1 kilobyte in size. With 64-bit pointers, we could theoretically reference around 24 quadrillion classes. And I'll go out on a limb and predict that a single application will not load 24 quadrillion different classes anytime soon. For this reason, the compressed class space is limited to 1 gigabyte by default and can be enlarged to up to 4 gigabytes using this option -XX compressed class space size. And to address 4 gigabytes, we only need 32 bits. Here you can see a slightly modified linear representation of the compressed class space. And a compressed class pointer is now a 32-bit offset into the up to 4 gigabyte compressed class space. The actual memory address of the metadata is obtained by adding that offset to the base address of the compressed class space. Here again is the previous illustration. And the compressed class space, which is at most 4 gigabytes, now holds approximately 5.6 million classes. That's significantly less than 24 quadrillion, but even large applications rarely load more than 100,000 classes. And that's why compressed class pointers are enabled by default, and there's simply no reason to disable them. Currently, this is still possible with the following VM option -XX minus used compressed class pointers. But it's practically never used, and that's why this option has been deprecated since Java 25. To summarize, a compressed class pointer is a 32-bit offset into the up to 4 gigabyte compressed class space within metaspace. And that concludes our visit to the compressed class pointers. Next, our journey will take us away from the pointers and toward object headers. A Java object consists of two parts in memory. The actual payload, meaning the object fields, for example, the x, y, and z coordinates of a point in three-dimensional space, and before that, the object header containing the metadata. The object header, in turn, is split into what's called the mark word, sometimes also referred to as the log word, and the class word. And mark word and class word are so important that they each have their own points on the map. We'll start with the class word. The class word is actually easy to explain. It contains the class pointer. And that used to be a 64-bit class pointer into the permanent generation before Java 8, and has since Java 8 been a 32-bit compressed class pointer by default. That is a 32-bit offset to the class metadata in the compressed class space within the metaspace. And thanks to this class word, the JVM knows at runtime which class an object belongs to. And there really isn't much more to say about the class word, which is why we can move right along to the mark word. There's actually quite a bit more to say about the mark word, so let me walk you through it in detail here. The mark word is 64 bits wide and contains the following information for every Java object. The identity hashcode, that's the value returned by system identity hashcode. It's 31 bits wide. The object's age, meaning how many times the object has survived a garbage collection in the young generation. That's 4 bits. At the end here we have 2 log bits, which we'll get to in a moment. Bit number 7 was used by the concurrent mark sweep garbage collector, which was removed in Java 17. And bit number 2 was for biased locking, which was removed in Java 19. And up front here we have another 25 unused bits. Here you can see the complete header, meaning mark word and class word. First in the standard variant with the 64-bit mark word and the 32-bit compressed class word. In total, that's 96 bits. And here in the variant that is marked as deprecated as of Java 25 with compressed class pointers disabled, meaning with a 64-bit class word, a total of 128 bits. Here you can see an example of a complete object, a long object. At the front, we have the 96-bit or 12-byte header consisting of the mark word and the class word. Then comes the payload, 8 bytes. And behind the object, when using compressed OOPS, the standard mode on 64-bit systems, there are an additional 4 unused bytes. And that's because from here to here, it's 20 bytes. But objects always lie at memory addresses that are divisible by 8. That means if the address here at the front is divisible by 8, then the next address divisible by 8 is not 20, but 24 bytes after the start of this object. And that's why we end up with 4 unused bytes at the back. So in total, 24 bytes are occupied. The header takes up 12 bytes, meaning 50% of the total memory footprint of this object. An integer object is 16 bytes long, that is divisible by 8, so we don't need any padding bytes here. And here, the 12-byte header takes up as much as 75% of this object's memory. Of course, many objects are larger than primitive wrapper objects. For those, the 12-byte overhead is less of a concern. In typical applications, most objects are between 32 and 64 bytes in size. And therefore, the overhead caused by object headers is usually around 20%. A few years ago, Project Lilliput was started with the goal of downsizing Java object headers to 64 bits or less, and thereby also reducing the overall memory usage of Java applications. But before we get to Project Lilliput, we need to look at what the mark word has been used for so far and why that has been an obstacle for the Lilliput team up to now. And that is synchronized locking, meaning the use of Java objects as monitors for critical sections. Here you can see an object on the Java heap with the object header, that is the mark word, followed by the class word and the payload. In the following, we will focus on just the mark word. With the classic implementation of synchronized, the mark word gets partially overwritten. When a thread enters a synchronized block, this is recorded in the mark word of the object being synchronized on. And here's how. On the stack of the locking thread, a data structure is created, the so-called basic lock. The mark word is copied into it, and then the upper 62 bits of the mark word are replaced by a pointer to the basic lock. And the lower 2 bits, the so-called lock bits, are changed from their normal state 0,1 unlocked to 0,0 locked. When the synchronized block is exited, the mark word is copied back from the basic lock into the header and the basic lock is deleted. Let me go back to the locked state once more. If another thread now tries to enter the synchronized block before the first thread has left it, the basic lock is replaced by a more complex data structure in native JVM memory, the so-called object monitor. The upper 62 bits of the mark word are then replaced by a pointer to this object monitor, and the lock bits are set to 1, 0. The object monitor again contains the original mark word and additional synchronization data, such as a list of waiting threads, which allows the JVM, as soon as the first thread leaves the synchronized block, to wake up one of the others. This transition from a basic lock on the thread stack to an object monitor on the heap is called lock inflation. And the state represented by the status bits 10 is called inflated. The entire mechanism I just described is called stack locking, or since it was replaced by a newer mechanism in Java 23, legacy stack locking. Legacy stack locking has two major disadvantages. First, as long as an object is locked, the information in its mark word can only be accessed indirectly via the basic lock or the object monitor. This makes, for example, reading the identity hash code more difficult. And second, if a virtual thread calls a blocking operation inside a synchronized block, is unmounted from the carrier thread, and later remounted onto a different carrier thread, then the stack of this thread resides at a different memory address than the stack of the original thread. And the pointer from the object's mark word to the basic lock becomes invalid. To prevent exactly this, the virtual thread is pinned to its original carrier thread while inside a synchronized block. And that in turn also blocks the underlying platform thread. This concludes our tour of the synchronized mechanism with stack locking, and along the way we have also learned one of the reasons for virtual thread pinning. To avoid all the issues just mentioned, that is, pinning and the extra effort needed to access the data in the mark word, and to pave the way for compact object headers, a new locking mode was gradually introduced starting with Java 21, the so-called lightweight locking. Here you can see once again the marked word in its unlocked state. When a thread enters a synchronized block with lightweight locking, the JVM, just like with legacy stack locking, sets the lock bits to 0, 0. But the rest of the mark word stays unchanged. Somehow the JVM needs to keep track of which thread is currently running inside a synchronized block. With stack locking, this was solved by storing a pointer in the object's header, the object being synchronized on, pointing to a basic lock on the stack of the locking thread. With lightweight locking, this basic lock and the pointer to the stack are gone. Instead, this information is stored in a fixed data structure at the beginning of the stack, the lock stack. There, a pointer to the monitor object is stored in the opposite direction. Only when contention occurs, meaning when a second thread tries to enter the synchronized block, an object monitor is created in JVM memory, just like with stack locking, and the lock bits are set to 10 inflated. But even in the inflated state, the address of the object monitor is not written into the mark word. Instead, it is stored in a global hash table, the object monitor table. The key is, this is a somewhat simplified representation, the identity hash code of the object, and the value is a pointer to the object monitor. This allows the JVM to find the corresponding object monitor using the object's identity hash code. And that's all there is to it. Lightweight locking has several advantages. Here you can see the uncontended lock again, and in most cases a lock stays uncontended. That means while one thread is inside the synchronized block, no other thread is trying to enter it. In this case, the overhead of creating an additional data structure is eliminated. The lock stack, after all, exists permanently. Secondly, the mark word never needs to be overwritten, neither in the uncontended lock nor in the lock with contention. This means that, for example, the identity hash code remains directly accessible through the mark word at any time and doesn't need to be read from the basic lock or the object monitor, as was the case with stack locking. And thirdly, back to the uncontended lock, virtual threads can now also, inside a synchronized block, be unmounted from the carrier thread and later be mounted onto a different carrier thread without any pointers becoming invalid, because the pointer now goes from the stack to the object. Lightweight locking is one prerequisite for virtual thread no longer needing to be pinned. A few more changes were needed, which were only implemented in Java 24, but those are not the topic of this talk. In Java 21 and 22, lightweight locking must be enabled via this VM option -XX locking mode equals 2. Starting with Java 23, lightweight locking is enabled by default. However, you can switch back to legacy stack locking using this VM option -XX locking mode equals 1. But then virtual threads will be pinned again. And that's why the option was immediately marked as deprecated in Java 24. That was lightweight locking. It makes the mark word essentially immutable. And this opened the door for the Project Lilliput team to make the header more compact, without having to account for temporary overrides caused by synchronized locking. And that brings us to the highlight of the journey: compact object headers. As a reminder, currently the object header is usually 96 bits in size. With disabled compressed class pointers, it's even 128 bits. But since this option has been deprecated since Java 25, we won't be considering it any further. Within Project Lilliput, work has been underway for years to shrink the header. And in Java 24, the first result from Project Lilliput was introduced initially as an experimental feature under the name which you already know, compact object headers. Compact object headers uniformly reduce the header size to 64 bits. As of Java 25, compact object headers are ready for production use. How is it possible to fit the information from those 96 bits into just 64 bits? Here you can see the precise structure of the previous header. We have the hash code with 31 bits, the object age with 4 bits, the 2 lock bits, and the compressed class pointer with 32 bits. Altogether, that's not actually 96 bits, but only 69 bits, because 27 bits are currently not used at all. To get down to 64 bits, we really only need to save 5 bits. But where can we save them? The Lilliput team experimented for a long time with various options, all of which had more or less negative impacts on performance. But in the end, they found a solution that comes with no performance trade-offs whatsoever, and that is a radical reduction of the class pointer from previously 32 bits down to just 22 bits. How does that work? Here you can see the status quo again. We have a 32-bit offset into the at most 4 GB large compressed class space in metaspace. With this offset, we can address every single byte position within the compressed class space. But that's not actually necessary. Similar to how objects with compressed OOPs can only be addressed in 8-byte steps, we can also address class metadata at larger intervals. Class metadata is, as mentioned, between 512 and 1024 bytes in size. What if we align them, for example, to 1024 byte blocks, as shown here? That is only to memory addresses divisible by 1024. 1024, that's 2 to the power of 10. And that means the last 10 bits of any 32-bit offset would always be 0. Which in turn means only the first 32 minus 10, that is 22 bits of the offset, are needed. And these 22 bits are exactly what we see here at the front of the new 64-bit header. With these 22 bits, we can now address 2 to the power of 22, that's about 4.2 million classes. As a reminder, with a 32-bit pointer, we could address around 5.6 million classes. So, despite saving 10 bits, we can, in terms of order of magnitude, address nearly as many classes as before. Here you can see the difference again. With 32-bit pointers, we can address every single byte. 22-bit pointers point to 1 kilobyte blocks. What you can also clearly see here is that the compressed class space is now fragmented and we have lots of free memory areas. But the Lilliput team considered that as well. Unused space may also be occupied by other metadata, so compared to the previous implementation, no memory is wasted. Back to the new header. Next to the compressed class pointer, we have the unchanged 31-bit identity hash code. The 4 bits for the object age are also unchanged. Likewise, the 2 log bits. Earlier I said we needed to save 5 bits. Through shrinking the class pointer by 10 bits, we now actually have 5 bits left over. Here 4 and another one here. This single one is still needed for the so-called self-forwarded tag. What's that about? Here you can see the old header again. The Lilliput team faced yet another challenge. Not only stack locking modifies the mark word, but some garbage collector algorithms do as well. When the garbage collector moves an object to another location, it first creates a copy of the object, including its header. Since a concurrent garbage collector like G1 or ZGC wants to keep stop the world pauses as short as possible, it doesn't update the references to the moved object during the stop the world pause. Instead, it does so concurrently with the running application. This means the object must temporarily be reachable at both its old and its new address. To achieve this, the upper 62 bits of the old object's mark word are overwritten with what's called a forwarding pointer, pointing to the new object. And to indicate the state, the log bits are used, because they still have one combination left, the 1-1. Once all object references have been updated, the old object, including its overwritten mark word, can simply be deleted. Sometimes, during garbage collection, a compaction failure occurs, meaning there isn't enough memory to copy an object to a new location. In that case, the garbage collector overwrites the mark word with a pointer to the object itself. This is called self-forwarding, and that's how the garbage collector marks that it has checked the object but hasn't moved it. With the compact 64-bit header, however, the important class pointer would be lost. And without the class data, the garbage collector doesn't know how large the object is. So an alternative to the self-forwarding pointer had to be found. I already hinted at the solution earlier. One of the 5 free bits is used for the new self-forwarded tag. If the garbage collector cannot move the object, it simply sets this bit instead of overwriting the entire header. And the 4 bits that are still left, they are reserved for Project Valhalla, that is for value object, but that's a topic for another session. Here you can see the complete compact object header. Mark word and class word are no longer separate parts, they've been merged into a single 64-bit value. To enable the new object headers in Java 25, you need to specify this VM option -XX plus use compact object headers. Before compact headers are enabled by default, the Lilliput team wants to wait for feedback first. But the job for enabling them by default is already in the pipeline. Now you've seen how compact object headers work and how, despite shrinking from 96 to 64 bits, all essential header properties have been preserved, and how even 4 bits could be freed up for future use. Now the question is, was this effort worth it? Do compact object headers provide concrete benefits in practice? And this question can be answered with a clear yes. The JEP itself mentions a reduction in heap usage of 10 to 20%. Amazon even reports 22%. Alibaba cites values between 5 and 10%. But besides saving memory, there's also a performance gain. Because when objects are smaller overall, more of them fit into the CPU cache, and memory accesses are less likely to cause cache misses, allowing the CPU to work more efficiently. Amazon reports 8 to 11% higher throughput. Reddit user Plokhotnyuk reports 10% more throughput in a JSON benchmark. And Alibaba reports 6 to 9% increased throughput. And the best part is, you don't have to change a single line of code to achieve these improvements. You just need to upgrade to Java 25 and set this VM option -XX plus use compact object headers. There are a few minor restrictions you should be aware of. First, you cannot combine compact object headers with uncompressed class pointers, which makes sense. With compact object headers, they are compressed even further. Also, that option has been deprecated as of Java 25 anyway. Second, you cannot combine compact object headers with legacy stack locking, which also makes sense because compact object headers rely on the fact that they won't be overwritten by synchronized locking. That VM option is deprecated as well. And third, the garbage collector's forwarding pointer. The pointer that's set from the old address to the new one when an object is moved, that one still exists. And with a compact object header, it gets written into the lower 42 bits of the header, so it doesn't overwrite the class pointer. With those 42 bits, we can address up to 8 terabytes, and that's why compact object headers are not compatible with a heap larger than 8 terabytes. This does not apply to ZGC because ZGC manages its forwarding information in a separate table. Now you've learned about the current state of Project Lilliput. And here's a brief outlook on Lilliput 2. The goal is to shrink the headers even further, down to just 32 bits. And there's already a concrete proposal for how that's supposed to work. You can find it in the Project Lilliput wiki. I'll give you a link to that at the end of the presentation. But be careful, there's a mistake here. One of the 4 H bits is currently missing from the diagram. I pointed this out to the Lilliput maintainer, and he confirmed that this is indeed an error. However, as of today, he hasn't corrected it yet. So here's a correct representation of the 32-bit header. Unfortunately, we don't have time today to go into the details, so just very briefly, the class pointer was shortened by another 3 bits, which is still enough for 500,000 classes, and if that isn't enough, the class pointer will be stored elsewhere. And the identity hash code is now only generated on demand and then stored at the end of the object. And up here at the front, we only have 2 bits which hold the status of this on-demand generation. It's currently not known when the first experimental implementation of 32-bit headers will be available. But 64-bit headers are already a reality today. So go ahead and turn them on. And with that, we have reached the end of this journey through the JVM. And I think this journey has impressively shown how the JVM, even after 3 decades, is still being consistently evolved and what substantial optimizations are still possible. And I think we're all very excited to see where this journey will take us over the next few years and decades. Behind the QR code, you'll find all the promised links and the slides. And if you're interested in more content from me, feel free to check out Happy Coders EU or one of the other channels. Thank you for your attention.